Dear students, I welcome you back in the fourth lecture of Unit 4 of Computer Organization and Architecture KCS 302 subject. Till now, we have discussed regarding the different type of memories, we have discussed regarding some replacement algorithms, and many more have been discussed in the previous three lectures. Here in the fourth lecture, we will discuss maximum about the virtual memory, what a virtual memory is, what are the different type of techniques to work upon the virtual memory, how are the different performance criteria to be followed while working with the virtual memory has been discussed in this lecture. So following are the some content which will be discussed over here. Virtual memories will be discussed, thereafter virtual memory organization, address translation schemes, different type of schemes, how the address will be translated from the main memory to cache memory, or you can say the virtual memory utilization. Parallelly, a performance enhancement, performance calculation will also be done with the help of hit rate and miss rate, or simply you can say miss penalty into that the system. If you are missing some content into the main memory, then it is called as the miss penalty. Similarly, as far as this is the new concept for you all the students, and similarly it's a important concept which must be known by you. The very background of this particular topic, the virtual memory, should be maintained before going into the subject, before going into the concept. I will discuss you what is the virtual memory. As far as the name is concerned, the term virtual can be defined as the something which is virtual to the system, which is virtual for the utilization. In other words, I will say, for example, we generally you might be here. You are very much aware that the size of the main memory. What will be the size of main memory? Nowadays, you can say 4 GB. You can say 8 GB, 6 GB, 2 GB. If you are saying the very high-end computers, then 32 GB RAM is again there in the servers. We are having in our big data lab, we are having 32 GB RAM systems. All the 30 systems are 32 GB RAM. Similarly, in the previous days or even nowadays, the size of the program is very heavy as compared to the size of the RAM. So for example, if you are having you are very much aware that every program which should be executed, which should be worked upon by the system or to be run on the system, that particular program should be come into the RAM. This is the basic concept of the, you can say, fundamental concept of the memory organization working on the system, or you can say these are the principles of the operating system. If a program is to be worked upon, then that program must be there into the main memory. If the size of that program is X bit, simply not take the X, we will take a constant number so that you can understand easily. If say we are working with a program that is having a size of say 20 GB or something, not 20 GB, you can say 20 MB. But we are using a main memory or simply a RAM with which is less than 50 or 20 MB. Say another example. We let's this particular laptop is of 4 GB. But if I am using a application heavier than the 4 GB, then simply you can say of 8 GB or simply of 6 GB or 5 GB, which is more than the size of my main memory, then what will be the case? My program will not be run, because the size of the program is larger as compared to the size of the RAM or simply the size of the main memory. So I can't execute, but you will experience that we are executing the program larger than the main memory size. It is no case. We are not in the position to run the program, because if you are having a laptop or a system which is having 2 GB RAM or 4 GB RAM, you can run a program which is larger in the size as compared to the main memory size. So what is the concept? By which concept, by which help you are executing these type of programs? These type of programs has been executed with the help of the concept that is called as virtual memory. What is that? Into this type of concept, by helping the virtual memories, we take only the size of the program which are being required at a particular time t into the main memory. Say example, I can break my particular program which is to be executed into the system into 2 parts, 3 parts, or 4 parts. For example, if I have to execute a program of 8 GB RAM with a capacity of a system having 4 GB of the RAM. For example, the size of the program is 8 GB, and the size of the RAM or size of the main memory, I will say the word main memory will be more suitable over here. The size of the main memory is 4 GB, and the size of the program is 8 GB. So as per as the system, it will not work because the size of the program is larger as compared to the main memory. What will be happen? We will divide that particular program into different type of clusters. What we will say, these clusters will be called as pages. The equal size of cluster, equal size of divisions will be called as the page over here. The size into which we are breaking a particular program will be called as a page, whereas the size into which we are dividing our main memory will be called as the frame. So we will divide the program into the pages, the program which is to be executed into the pages, and the memory into the frames. These frames will be filled with the pages. So many of number of required of the pages will be come into the maximum required pages will be taken into the main memory. Remaining ones will wait to their turn. For example, I need only some amount of the data which will be taken to the main memory. The remainings will be there into the auxiliary memory or the secondary memories. When the requirement of the another pages will be required, then the previous page will be replaced and the new pages will be taken into the main memory. By this way, we can execute the complete 8 GB program. For example, I will take a very simple example. Let 8 GB. It is very analogy. It is for example only. Don't quote it as the size. As per as the size, I am taking to make the system, to make the concept very simple. Say I am taking a example of 8 GB and 4 GB only. My program size is of 8 GB and my laptop size is of 4 GB. So I have to execute this program which is larger as compared to the size of my main memory. What I will say, I will divide all the size of that program into, for example, 1 GB page size. However, the page size is not so large of 1 GB, but I am taking it only for the sake of example. Let's take this particular 8 GB as the is divided into 8 equal clusters, or simply we can say 8 equal pages of 1 GB each size. So we will take 4 pages. We can take 4 pages at a time because 4 GB is the maximum size. Or we can say we can take at a minimum time t, we require only 2 pages. We will take those 2 pages into the main memory. We will work upon that. We will execute those. The remaining 6 pages will be there. We will replace those previous 2 pages with the another 2 or 3 or 4 pages into the main memory. So by that way, by placing the new pages and replacing the old pages, we can work upon with this 4 GB system only. So this is the very basic background which should be clear before starting this virtual memory concept. Here in the main memory is smaller than the address space. For example, if we are having a processor of 32-bit address only. For example, if the address bits of the processor are 32, so how much we can make the space? We can address up to the 4 GB of the space. But main memory may only be few hundreds of the megabytes. It's the example of the previous time when the RAM was of only megabytes. But in nowadays we can work upon with the gigabytes as the RAM. Parts of the program not in the main memory stored on the secondary storage device such as this. As I told you, the remaining parts of that particular program will reside into the secondary storage. Only the part which are being required, which are necessary to take into the main memory, will be taken into the main memory. So techniques that automatically move program and data blocks into the physical main memory when they are required for execution are called as virtual memory techniques. For example, I have to work with some pages. Those required pages will go into the main memory, other will reside into the secondary memory. At the time when the pages which are residing into the main memory have been completed, their work have been completed, then those pages will be replaced and the new pages will come into the memory. Similarly, operating system moves program and data automatically between the physical main memory and secondary storage virtual memory. As far as this particular is concerned, this is the simple diagram as far as of the memory hierarchy, as we have discussed in the previous lectures. This is the virtual memory organization, how the particular system is working. Simply you can say this is a type of memory hierarchy we have discussed only. It has been organized with the virtual memory only. In the end, we are having the disk storage, then direct memory access, transfer of the data. Thereafter, the data will go into the main memory. And after that, for the faster memory, transfer memory, that is called as cache memory. And with the help of memory management unit, that is MMU, it is working with the processor. So processor required data, you know it is required the data into the main memory before working. Every time you have to work upon or you have to read or write operation is to be done with the memory, then that particular data is required into the main memory by the processor. So processor can only read or write with the help of main memory, that is the RAM. So that should be organized. That particular work is of MMU, that is called as memory management unit. So over here, simply to make the concept very simple, I can say if I'm saying that disk storage is the superset, then main memory is the subset of disk storage. Thereafter, this cache is the subset of main memory. And simply you can say the registers are the subset of cache memory, and the process is working upon with the help of registers and the cache memory. This all has been discussed into the concept theoretical part, which has been written over here. This is the memory management unit, translates virtual address into the physical address. If the desired data or instruction are there in the main memory, they are fetched as described previously. If the desired data or instructions are not in the main memory, they must be transferred from secondary storage to the main memory, as I have discussed. So all what I have discussed has been written over here. So I again advise to go through some books parallelly when you are listening, when you are viewing these type of lectures. So as far as the address translation is concerned, what is the meaning of, what is the requirement of address translation? The requirement of address translation is that every time we are working, we are transferring the data from main memory to the auxiliary or auxiliary to the main memory, because I told you that only the pages which are being required, which are necessary to be taken into the memory or simply into the main memory will be taken. Otherwise, the rest of the pages, rest of the cluster of that program, that very program will reside into the secondary memory, auxiliary memory. So addressing of every page and the process must be done because we have to address which type of cluster, which one of the cluster, because for example, I am taking only the 8 pages. It is only for example only. But in the real picture, if we will divide a 4 GB or 8 GB of the program, then it will be having thousands of the pages to be taken into the memory and to be taken into the back into the secondary memory. So a addressing scheme, a address translation scheme must be there so that we can make which page has been taken in and which page has been taken out. As far as this concern, assume that the program and data are composed of fixed length unit called pages. As I have told you, a page consists of a block of words that occupy contiguous location in the main memory. Contiguous location in the main memory. You have to be very vigilant by using this particular term, contiguous allocation. Page is page is a basic unit of information that is transferred between secondary storage and the main memory. Size of page commonly ranges from 2K to 16K nowadays, but the size of page can be larger, can be more with this size. Each virtual or logical address generated by the processor is interpreted as virtual page number, that is high order bits, plus offset, that is low order bits, that specifies the location of the particular byte within that particular page. As far as address translation, it is continued over here. Information about the main memory location of each page is kept in the page table. So I have discussed that I have given you a new term that is called as page. Another term is called as frame. There are two terms. One is term as page, another term is as frame. Where will be the frame are? Frame means the division of main memory. Equal size of frames will be divided. The main memory will be divided into the equal size of frames, and the program will be divided into the cluster, equal size of cluster, that is called as pages. So here the table which consists the information, which keep the information of the location of the page, it is being there into the page table. Information about the main memory location of each page is kept in the page table. Area of main memory that can hold a page is called as page frame. Starting address of the page table is kept in the page table base address register. Page table entry for the page includes what are the different terms which a page table entry required. It required address of the page frame where the page reside in the main memory and some control bits. Virtual page number generated by the processor is added to the content of the page table base register. A base register is there which consists the base value of the page number into the page table. Next, this provides the address of the corresponding entry in the page table. The content of this location in page table give the starting address of the page if the page is currently in the main memory. So this is the very simple example by which you can understand very easily. This is in the very you can say middle. I will show you with the annotate feature of this. I am taking the spotlight. So this is the page table. Here is the page table. It consists of some control bits and the page frame in the main memory. So starting from over here, this is page table base register. Page table base register holds the address of the page table. This is the page table address. Page table base register plus virtual page number provide the entry of the page in the page table. So when we are adding page table base register plus virtual page number, then what will be there? It will provide the entry of the page in the page table. This will provide the entry to the page table. Page table holds information about each page. This page table keep the information. It holds the information about the every page. This includes the starting address of the page in the memory. And over here, virtual address is interpreted as the page number and the offset value. Here, from here, this offset will be here, and this physical address will again come into the as a offset. So from here, this is the page frame. Physical address in the memory will consist of page frame and offset, and virtual address will consist of virtual page number plus offset into the page table. So by this way, by this process, by this address translation process, you can see how a page table base register plus the virtual page number can be entered into the page table as a page number. So this particular process can be discussed, but I will advise you again to go with some books, because this is however, it's a very simple concept, but to understand the concept, a few books or a re-listening of this video is being required. As per as address translation, page table entry for page also includes some control bits, which I have discussed in the diagram. You can see these are the some control bits over here. These are the control bits. Page table entry for a page also includes some control bits, which describes the status of the page while it is in the main memory. It describes the status. What are the status? It is a ready running state, or it is something is written into that particular or not particular, or reading from the page. So this is the status which describe the status of the page while on the time when it is there into the main memory. The page table information is used by memory management unit for every access. So it is supposed to be with the MMU, which consists of the page table entries that correspond to the most recently accessed page. A small cache called as translation look-aside buffer, that is called as TLB, is included into the MMU. What TLB consists of? TLB holds page table entries of the most recently accessed page. In addition to the above, for each page, TLB must hold the virtual page number of each page. This is again a virtual address calculation from the processor side. You will see this will tell you whether the data will be provided, or it will be called as the hit, or if not provided, it will be called as miss. If it is equal to, then it is hit. If the number is not equal to, then it is called as no, then it is called as miss. What is the meaning of this equal to? If the address is matching, if the address required or the address required by the processor and the content address available into the main memory or cache memory is equal to, then a match will be called. If the matching is okay, if the matching is yes, then we will say the data is available and will be called as hit. If the match is not equal to, means the address required by the processor and address of the content available in the main memory are not equal to, then it is called as no. So we will say the request has been missed. So this complete has been discussed over here into this diagram. You will see over here, this is TLB, transit look buffer. Over here, these are some control bit, virtual page number, page frame in the memory. This is virtual page number and the offset. By this way, it calculates whether this virtual page number and this particular value which is there into that TLB are equal or not. If yes, then it is hit. If no, then it is no. So you can say this is translation look aside buffer. By this way, this TLB will provide the information. Translation look aside buffer will give the information about this particular. As far as the address translation scheme is there, we are again with the process of this. 1 minute, please. This address translation is again continued over here. If a program generates an access to the page that is not in the main memory, a page fault is occur. As I told you, that is called if the value is miss. There are two terms, hit and miss. If the content is available, then it is called as the hit. If the content is not available, then it is called miss. If an miss has been occurred, then it is called as the page fault. Page fault means the page has been not received into the main memory. Upon detecting a page fault by the MMU, that is memory management unit, what are the different actions will be occur? Following actions will be occur. MMU asks the operating system to intervene by raising an exception. An exception will be generated. Processing of the active task which caused the page fault is interrupted. Control is transferred to the operating system. Operating system copies the requested page from secondary storage to the main memory. Once the page is copied, control is returned to the task which was interrupted. So this is the complete process which will be taken, which will be performed. When it will be performed, if the page is not found into the main memory, then it is called as page fault. What are the different operations will be hold when the page fault is occur? These are the some terms which I have told you. Processing of the active task which caused by the page fault is interrupted. Control is transferred to operating system. Operating system copies the request from the secondary storage to the main memory. Once the page is copied, control is returned to the task which was interrupted. Different performance considerations are there which should be keep into the mind. A key design objective of computer system is to be achieve the best possible performance at the lowest possible cost. Every time we are working with the price performance ratio. In the very less price, we want maximum performance. So for every system, for optimization system, every time we are looking a high performance with a low price. So price performance ratio is a common measure of the success. Performance of a processor depends on how fast machine instruction can be brought into the processor for execution. How fast the instruction can be executed. These are the some terms I have told you already. Hit rate and miss rate, or simply miss penalty. The success rate in accessing information at various level of the memory hierarchy can be calculated with the hit rate upon miss rate. Simply whether we will say it will be hit or a miss, we can say whether hit will be there or miss will be there. So this can be calculated with the hit rate or the miss rate. A miss cause extra time needed to bring the desired information into the cache. You can the concept is very clear. If the data is not found, it will take the maximum time because it have to be copied from the secondary to the main memory. I have told you what are the different steps, what are the different procedures which will occur if a miss is there. If the miss is there, then the term that the program which was running will be interrupted. The control will be transferred to the operating system. What the operating system do? The operating system will transfer copy the content from the auxiliary memory, secondary memory into the memory, main memory, and then again that particular transfer the control will be given to the task which was interrupted. So the time into the miss are more as compared to hit. A miss cause extra time needed to bring the desired information into the cache. Hit rate can be improved by increasing the block size. If we are increasing the block size, by that way we can improve the hit rate. While considering the cache size, that is T average is equal to HC plus 1 minus H into M. Here T average is access time experienced by the processor. H is hit rate, M is miss penalty, the time to access information in the main memory, the extra time if a miss has been occurred. Thereafter C, the time to access information in the cache memory. Again, cache on the processor chip. There are two type of cache. There are two type of cache memories. One is level 1 and level 2. Two separate caches for instruction and data or single cache for a both. The advantage of separating cache, what are the advantages? Because the parallelism will be there. If we are using the two type of cache, then the parallelism, or you can say the better performance can be achieved. Level 1 and level 2 cache are used in high performance processor. L1 cache are faster, smaller, access more one word simultaneously at and let the processor use them one at a time is one of the processor chip. L2 cache, slower and larger, may be implemented externally using the SRAM chips. Average access time, T average can be H1 C1 plus 1 minus H1, H2 C2 plus 1 minus H1 into 1 minus H2, that is M. Here you can be, here the terms can be given as H1 is hit, C1 is the cache level, again M is the miss penalty. So by that way, you can see the C is the time to access information in the cache. You can say H1 is the value that a hit rate is there. C is the time to access the information in the cache, and M is the miss penalty for information. M is the time to access information in the main memory. As far as the other performance enhancement are there are different type of performance enhancement, that is write buffer, write through. Each write operation involve writing into the main memory. If the processor has to wait for the write operation to be completed, it slows down the processor. Processor does not depend on the result of the write operation. Write buffer can be included for temporary storage of the write request. Processor places each write request in the buffer and continues execution, and write back block is written back to the main memory when it is replaced. What is prefetching? To enhance the speed, to enhance the performance, we required, because whenever we are the processor, every time processor have to wait if we have to read something. If we are reading that particular, if we are pre-reading that particular information, prefetching that particular information, then our processor will not have to wait. So prefetching is the concept where we fetch the data previously, proactively, before the processor is going into required that particular data. So simply the new data are brought into the processor when they are first needed. Processor has to wait before the data transfer is complete, so prefetching is being required. Prefetch the data into the cache before they are actually needed or before a read miss occur. Prefetching can be accomplished through the software by including a special instruction in the machine language of the processor. Inclusion of prefetch instruction increase the length of the program. Prefetching can also be accomplished using the hardware circuitry that attempts to the discover pattern in the memory reference and then prefetches according to this pattern. That is again here lookup free cache. So prefetch scheme does not work. There are some demerits of the prefetch as well. Prefetch scheme does not work if it stops other access to the cache until the prefetch is completed. Obviously, if we are using the prefetch operation, then it will block other access to the cache. So what will be here? A cache of this type is said to be locked when it is service a miss. So cache structure which support multiple outstanding misses is called a lookup free cache. Since only one miss can be serviced at a time, a lookup free cache must include circuits that keep track of all the outstanding misses. Special registers may be hold the necessary information about these misses. So as far as I have discussed in this lecture, I have discussed what the virtual memory is, how the address translation has been occurred, what are the miss penalty, what is the hit ratio, what is the hit rate, what are the miss penalty, and what are the different performance criteria on which a memory working has been worked. Similarly, we have discussed prefetching, we have discussed the lookup free cache. So as far as this chapter is concerned, I have to discuss some auxiliary memory, storage memory into this particular unit 4. Otherwise, maximum of the topics, maximum of the concepts of unit 4 has been covered till the lecture 4. In the next lecture, in the lecture 5th, I will discuss only some topics of the secondary storage memory. Otherwise, the chapter has been completed. I would again advise you to consult some of the books like Maris Mano, J.P. Hayes, or some other books. If, a book of your choice you can also take. So I'm again repeating, the reference or the go through of some book is mandatory to understand these type of topics. So with these words, I thank you all for your recent listening.